Hey class, it's me. I want to go through now some of the stuff related to the normal distribution that you'll see on Module 2, and specifically look at doing it in StatCrunch. I just have my calculator pulled up for some little calculations I'll be doing, but I'll be showing you how to do the normal probabilities in StatCrunch. We won't be looking at any tables at all. So, okay, first off, we're looking at this question, the area to the left of z. So, all right, well, let's just pull up StatCrunch and we'll look at the normal probability calculator there. It'll take a moment to pull up. Now, you can use Z tables. You can use Excel, TI-83 calculators, for example. Any number of forms of technology can help you do this. But since we are here, it's good to just feel comfortable using StatCrunch for all of this calculation, so I'm going to show you how it's done here. So let's pull it up under the Stat menu. You'll see Calculators. Under here, there is the normal calculator. So whenever you're dealing with calculating a probability with Z, capital Z, that's referring to a standard normal distribution, which means that the standard, unfortunately, they use standard here. Standard meaning to the left or to the right. But what we want to do is make sure that the mean and the standard deviation are 0 and 1 respectively. So that refers to a standard normal distribution. The mean of 0 and a standard deviation of 1. So if we're ever talking about the distribution of Z, it's a standard normal. Mean 0, standard deviation 1. So now we're looking at the area to the left of 0.24. So with this calculator, you put in this 0.24 down here and hit compute, and it'll calculate the probability. Let's copy it down 4 decimal places. I'll just copy 4 decimal places. And that's it. And you can see that the shading is nice and helpful also. The area to the left of 0.89. So you can see how that's done. It's you just put in the value. You don't have to do any sort of complicated calculation by hand. I'm going to have to round that up to 8133, so I'll remember that. 8133. This is much more exact than you're going to get by a table, and it's much faster, and you're less prone to error. 1.06, so 1.06. So you just type in the amount. I'm going to the left of 1.06, and to the left, compute 0.8554. Okay. I'm going to, this last part, it's the same thing. I'm not going to spend my time on that right now. Leave the question, that's fine. Okay, now if you want to do the area under the normal curve between, now the standard, you can switch the direction of inequality to be greater than or less than, depending on if you want to go to the area for the area to the right or the area to the left. If you want to do the area between two numbers, just click on this option here, and we can put in the two values, negative 1.28 and positive 1.28. So negative 1.28 and positive 1.28. Again, since I'm doing Z, it's a standard normal. The mean is 0, the standard deviation is 1. Let's compute that. And you know what I'm going to do? I'm going to pull this over so I can see both windows at the same time. Okay, cool. 4 decimal places, 0.7995 rounded up that last decimal place. Okay, between negative 1.11 and Z equals 0. So you don't be confused that this is using general X, but because we've set the mean at 0 and the standard deviation at 1, they can call it whatever we want. We know it's a standard normal. Okay, so far so good. Very, very easy to do once you realize how to use the tool. I'll skip this last one again. This is pretty simple. Okay, the total area under the standard normal curve, part A through C. Let's see, the area under the normal curve to the left of -2 plus the area to the right of z equals 2. So, okay, let's just do it in pieces. Let's do to the left of -2, calculate that. And you know what I'm going to do? I'm going to just add them up in the calculator here. So this is 0.02275 plus, let's do the next one, the area to the right of +2. Hey, it's the exact same thing. I actually knew that was going to be the case, but I'm going through just for argument's sake. Because what you could do is you could do it a couple ways. One, you know that because the normal distribution is symmetric, whatever the area is to the left of -2, you just double it to get the area in both tails. The other thing you can do is you can go the area between -2 and +2, and see that what I'm going to do is I'm going to take 1 minus this 0.954499, whatever it is, 997, oops, 9974, okay, 0.0455. So what I did is to get the area in the tails, I subtracted the area between them from 1, which is the total probability. So you could do it either of those ways. Either way, you get 0.0455. 0.0455. Okay, so now this one's a little bit different. It's asymmetric, so now the only way to really do this one is to just do them in the two parts. The area to the left of negative 1.52. Okay, we'll get that number in here. It's 0.064255. Okay, plus let's do the area to the right of 2.52. Okay, 0.00587. I'll just round it up a little bit. Rounding error is not going to kill me at this level. So here's what I've got. The total is 0.0701. Nice. Okay. All right. I'm going to skip this next one. After those two, you can see how you do the next one. So let's see. For number 7. Okay, this is good. Now this is very easy to do with the standard normal calculator. I'm looking at for a mean of 50 and a standard deviation of 7. So now I'm going to put in 50 for the mean, and the standard deviation I'm going to put in at 7. And the probability that x is greater than 34, you just type it right in here. 34. Hit compute. It'll give you the picture. It'll give you the probability, which are both things we need. And so, oh, this is nice. You can turn on these ticks for the various standard deviations or not. Anyway, but you can see clearly, like this is the picture that matches, and I imagine they're going to ask us what the probability is right here. 0.9889. We have to round that up. 0.9889. Okay, look at that, pretty good. For number 8, I think this one is looking for area between. Again, that's pretty simple, but let's just do that example. I'll keep the mean at 50, the standard deviation at 7, and put in my two values, 34 and 66, compute, and it gives you it shades it in, and it gives you the probability. So that's how you do that, pretty good. Now let's see, now for number 9, this is an application of normal probabilities. So we're told that the distribution on hybrid cars, let's see, the mean is 56, the standard deviation is 3.3, and so if we assume normal distribution, let's put this stuff in, 56 miles per hour, miles to the gallon, 3.3 for the standard deviation, and what proportion of hybrids get over 60 miles per gallon? So over 60, enter, compute, same thing. There you got your probability right there in the tail. 0.1127, 53 miles or less. Well, you turn this around for 53 miles or less, 53. 0.1817 and between, and then for between you just go to the between and you type it in. Super easy once you know how to do it. Very quick, no need to mess around with normal tables. Just make sure that you've typed it in all right. 59.62 and less than 45. Okay, I'll skip that last one. That's the same, more of the same. Okay, great. Now we're going to do some calculation. I'm going to do this straight in the calculator because there's not really a good, StatCrunch isn't really doesn't have a very pretty calculator function in it. Okay, but to calculate the sample for the sampling distribution, if you know the population mean and the population standard deviation, the sample mean is going to follow a distribution with the mean of its distribution will always be the same as the population mean. The standard deviation, on the other hand, will be smaller, and it will be smaller by the square root of the sample size. So the square root of 36, I have to divide it by. So these are nice numbers. It's actually divisible by 6, but no harm in using the calculator for that.
Okay, so now we have, let's see, suppose the length of pregnancies of a certain animal are approximately normally distributed with a mean of 151 and a standard deviation of sigma equals 8 days. Okay, so the probability that a randomly selected pregnancy lasts less than 148. So we're not talking about a sampling of more than one, so I'm going to pull up again that normal probability calculator in StatCrunch. For the distribution of a single observation, it's going to simply be a normal distribution with this mean of 151 and a standard deviation of 8. And so when we're looking at the probability that pregnancy lasts less than 148, we're looking for the probability that this random variable is takes a value less than 8. So it's under the calculators, again, stat calculators normal. And I just have to put in the mean and the standard deviation. Let's move this a little bit to the left so we can see both. Okay, the mean is 151. Standard deviation is 8, and we're looking for the probability that the pregnancy is less than 148. Well, that 0 shouldn't be there. Okay, great. This is the curve, this is the picture. We've got a probability of 0.3538. I'm just going to copy that right from here and paste it in. Beautiful. Now we're doing a random sample of 18. So when you do a random sample of 18 and the probability that the sample mean is less than 148, the standard deviation is not going to be 8 for the sampling distribution. Remember, the sampling distribution has a standard deviation of 8 divided by the square root of the sample size. So this is going to be the standard deviation on my sampling distribution. Okay, put in 1.8856. I'll just put in a few decimal places. But we're still looking for, we still have a mean of 151. That doesn't change. And we're still looking at the probability that the sample mean is less than 148. So that's going to be the same. So the probability is a lot less, which is what we'd expect. It's much less likely that the mean of 18 samples is going to be extreme than a single observation is going to be extreme. So copy these 4 decimal places in. Okay. What's the probability the random sample of 35 has a mean of 148 or less? Okay, so the only difference now is this standard deviation is going to be even less. So let's do 8 divided by the square root of 35. 1.35. 3522. Okay, and we're still looking at the probability of being less than 148. Now the probability is even less. Okay, so I'm going to copy those over, but I have to round that up to 3.3 because it's just a little bit over half. Okay, great. Let's see, the shape of the distribution of the time required to get an oil change at a 10-minute oil change facility is unknown. Okay, so however, records indicate that the mean is 11.2 minutes and the standard deviation is 3.5. Okay, compute the probabilities regarding the sample mean using a normal model. What size would be required? To use a sample. So, okay, this question is getting to a rule of thumb that you see in book after book, that the rule of thumb is if we have more than 30, then we should be able to use a normal distribution. Now, the jury is out on whether this is actually a legitimate rule of thumb, but this is the rule of thumb we'll continue to use because we have to have some point. In fact, there's other methods that can get a better estimate of how big of a sample size you need, but at any rate, at least 30 or more, and we should be able to use a normal distribution for our sample distribution, right? So now we're looking at the probability of a random sample of 40. Okay, so going back here, the thing we need to calculate is the standard deviation on a sampling distribution. So 3.5 divided by the square root of the sample size of 40. Okay, so there's the standard deviation on the sampling distribution of the sample mean. So let's put all this stuff in. So 0.5533. I'll just round it up to 3.4. And the mean, it says the mean is 11.2 minutes. That was up top, 11.2 minutes on average. For a single oil change, the standard deviation is 3.5, but the average of 40 oil changes, the standard deviation is going to be a lot less. So now we're looking for the probability that the sample mean is less than 10. So I'm going to change this to 10. Compute that. Beautiful. That's the probability, 0.0151, rounded up because that's 6. Beautiful. Okay. Let's see. Describe the sampling distribution of p hat assuming a sample size of 20,000. Now okay, so for the sample proportion, so first of all, when you're doing a sample and you're trying to estimate the sample or the population proportion, the sample proportion, you can use a normal distribution as long as your sample size is big enough to that you'll have a certain number of people saying yes and saying no in expectation in your sample. So the rule of thumb is as long as your sample size isn't too big, let's go back to our calculator. 0.05, let's clear this, 0.05 times the population, 20. As long as your sample size isn't more than 1,000, that would be too big of a sample. And as long as we would expect, we would get this number comes out to be 10. So this is our sample size, 800 times p.6 times 1 minus 0.6, 192. So as long as we have at least 190, so as long as this number here is greater than 10, and as long as 1,000 is greater than, or sorry, as long as our sample is smaller than that 1,000, we're in good shape. So it's approximately normal because of that. Too big of a sample and our sampling stops being independent of each other, and too small of a sample is just too small of a sample for the central limit theorem to work. So the mean for this sampling distribution will be the same as the population proportion of 0.6. The standard deviation follows a formula. It's the sample size. Sorry, it's going to be the square root of p, that's 0.6, times 1 minus 0.6, p times 1 minus p, divided by the sample size. Everything in this whole fraction, I'm square rooting the whole thing. So this is the formula for to find the standard deviation for the sampling distribution of p hat. It's the square root of the fraction p times 1 minus p divided by n. Okay? So let's type it in 173, 3 decimal places, 0.017. And with that, oh, we aren't asked for probabilities. Okay. Okay, well, let's see. We've got the same kind of a question. Sample size of 125, a population of 15,000, p is equal to 0.2. Let's check if this is approximately normal. So at 0.05 times 15,000, 750. Is our sample size smaller than that? Yeah, it is. 125 compared to 750. Let's check the other thing. 125 times p, which is 0.2, times 1 minus p, 20. As long as the sample size is at least 20, but not the sample size. As long as we get this number bigger than 10, and as long as the sample size is smaller than that 750, we're in good shape. So it is approximately normal because little n is smaller than this, 750, and because this number 20 is greater than or equal to 10. That's what we want. Sorry, so it's B is the answer. So once again, 0.2 for the mean of this distribution, the standard deviation, it's square root of p, 0.2, times 1 minus 0.2 divided by 125. 0.036 rounded. Oh, 6 decimal places. Holy cow. 5777. Okay, those are 6 decimal places. That's what you wanted. That's what you get. Okay, now we have a probability question. So now we're going to go back to our normal distribution, and we're going to put the mean in at 0.2, the standard deviation in at 0.035777. Since I have all the decimal places, I might as well use them. Now we're looking for the probability that p hat is greater than or equal to 0.24. Compute, and then we got it right there. This is our probability. Take 4 decimal places. I'll have to round that up. Change that to an 8, and we got it. Last part, the probability that, so what's the probability that p hat is less than or equal to 0.12? Okay, well, we have everything here. It's just a matter of changing the direction and changing this to 0.12. And there's our probability. And again, I'm going to have to change that 6 to a 7 to round it up. Okay. Great. All right, so that's how we use the normal probability calculator when we find the sampling distribution for our sample mean and sample proportion.